Hello everyone, welcome to my channel. Now in this question it is said that the geometry around tellurium in the symmetrical trimeric species of TeO2F minus is. So we have this compound TeO2F minus and the geometry for this compound is asked in the symmetrical trimeric species. So let's not focus on this trimeric species first. So let's focus on this compound. So in this compound, the central atom is Te, tellurium, belonging to the oxygen family. So the number of valence electrons should be Ns2, Np4. So total 6 electrons. Okay. Then the number of electrons which are contributed from other atoms, we have 2 oxygens and 1 fluorine. So 2 and 1, 3, and also we have a negative charge. So total number of electron pairs should be, it is 6 plus 3 and 1 negative charge. So divided by 2, so 10 by 2 is equal to 5 electron pairs. And 5 electron pairs belong to which kind of hybridization in VSEPR theory? So it belongs to sp3 dehybridization, which gives the regular geometry as trigonal bipyramidal, also known as TBP. Now here one question arises that why we considered the contribution from 2 oxygens if it has any probability of double bonds, because we saw in earlier questions that VSEPR does not consider the double bonds, only sigma bonds are considered. So here we consider the contribution from O2 because here it is given the symmetrical trimeric species. That means if TeO2F exists as trimeric species, then it should be Te3O6F3 minus 3. That means oxygen is connected to the neighboring oxygens through a bridge. So in the trimer, other oxygens are also present nearby and connected through bridges. Then that's why the possibility of the double bonds is extremely low, and that is why we have considered the contribution of O2 in the calculation of the electron pairs. So now what we have got by counting the total number of electron pairs is the parent geometry or the electronic geometry. So this formula TeO2F minus we used to find out the total number of electron pairs around the central atom using the VSEPR concept. And from here what we get the typical total number of electron pairs, which determines the ideal hybridization and the ideal geometry, which is also known as the parent geometry or the electronic geometry. Now, after doing this, then we focus on the symmetrical trimeric part. Now, from here, if this molecule attains a symmetrical trimeric part, that means trimeric we have Te3O6F3 all in the multiples of 3 and 3 minus. Okay, so the symmetrical trimeric part becomes Te3O6F3 3 minus. Now, if we try to draw the structure of this symmetrical trimeric form of this molecule, then it means we have an alternate tellurium oxygen kind of structure. Okay. So we have a structure something like this, which is the symmetrical trimeric TeO2F minus. So we have tellurium alternating with the oxygen, and you can see the oxygen are bridged. Okay. And if we consider tellurium, we can see it is connected to 2 bridged oxygens. Okay. So these are the bridged oxygens. And then we have a terminal oxygen and a terminal fluorine. So now if you look at this structure, then you find that the central atom tellurium, so this is the central atom which is connected to 4 or which is bonded to 4 atoms, 2 bridged oxygen atoms, okay, 2 bridged oxygen atom, 1 terminal oxygen atom and 1 terminal fluorine atom. So there are 4 bonds around each tellurium atom. Okay. So each tellurium atom is having 4 bonds. That is, it is connected to 2 bridged oxygen atoms, 1 terminal oxygen and 1 terminal fluorine atoms. That means from this symmetrical trimeric structure, we can visualize that there are 4 bond pairs for tellurium. Okay. So tellurium has 4 bond pairs. Okay. Now, if tellurium has 4 bond pairs, then what is the number of lone pairs in tellurium? So if we go back, then we see that the total number of electron pairs in tellurium was 5. Okay. So to find out the number of lone pairs, we subtract the total number of electron pairs minus number of bond pairs. So we have 1 lone pair on tellurium. Now, if our parent geometry is TBP, and in this TBP, if we have 4 bond pairs and 1 lone pair, that means it is not an ideal trigonal bipyramidal, but a distorted or a pseudo-trigonal bipyramidal geometry. And to be very precise, when we have 4 bonded pairs and 1 lone pair in a parent trigonal bipyramidal geometry, then we have the molecular shape as seesaw. If you go back to the principles of VSEPR theory, then you will come across this principle that in an ideal trigonal bipyramidal geometry, when we have 4 bonded pairs and 1 lone pair, the molecular shape is, the actual shape of the molecule is a seesaw. And now to understand this seesaw shape, you have to look at this structure, the symmetrical trimeric structure. You can see that tellurium is connected to 4 bonds. So in an ideal TBP geometry, we have 3 equatorial and 2 axial bonds that you know very well. So the 2 oxygen atoms are occupying the 2 axial positions. 1 fluorine atom occupies the equatorial position. The 3rd oxygen atom, okay, so we have 3 oxygen atoms, as you can see, 1, 2 and 3 around tellurium. Okay, so let us suppose that the 3rd oxygen atom is occupied at the equatorial position, and now, so these 4 bond pairs are now satisfied in this structure. Okay, and now the one and only lone pair occupies the equatorial position, something like this. Okay, now why this lone pair occupies equatorial position? The lone pair occupies the equatorial position in order to minimize the lone pair bond pair repulsion according to the VSEPR theory. Okay, and make the structure stable. So this is our seesaw shape for the symmetrical trimeric TeO2F minus structure. So if you want to visualize this seesaw structure, so we do not indicate the lone pair. So this is tellurium. So something like this, we have 2 axial oxygens, then 1 equatorial fluorine and 1 equatorial oxygen, which shows the similarity of a seesaw. So this one is the actual molecular shape of this compound. Now going back to the question, we have an option of square planar. No, it is not a square planar structure. Tetrahedral, no. Trigonal bipyramidal and octahedral. No, it is also not octahedral. So in all probability, the structure of this compound is trigonal bipyramidal. That is the actually not exactly an ideal TBP, but the parent geometry, what we attain from calculating the total number of electron pairs, is an ideal TBP structure. And then it distorts into a pseudo trigonal bipyramidal and actually a seesaw molecular shape. So third option is our correct answer, trigonal bipyramidal, although it is a pseudo trigonal bipyramidal. So I hope this explanation was clear to you. It is not a straightforward answer. First, you have to calculate the total number of electron pairs by applying the VSEPR theory, and then you have to focus on the question which says symmetrical trimeric species, because this particular compound chemically it does not exist in isolated form. Okay, And that is why the question specifically says symmetrical trimeric. Now, after calculating the total number of electron pairs around the central atom and determining the ideal geometry, then we move on to the actual structure, that is the symmetrical trimeric structure. And from here, we understand that tellurium, each tellurium is surrounded by 4 atoms. Okay. And that means it has 4 bonding pairs. 1 terminal oxygen, 1 terminal fluorine and 2 bridged oxygens. Okay. That accounts to a total of 4 bond pairs. And from there, we find out the number of lone pairs to be 1. And in the ideal trigonal bipyramidal scenario, when we have 4 bond pairs and 1 lone pair, then we have the seesaw molecular shape or molecular geometry that we have drawn here, that how we have this seesaw shape where the lone pair occupies the equatorial position in order to minimize the lone pair bond pair repulsion. So I hope this explanation is clear to you. And if you find my videos helpful, please like, share and subscribe. And please let me know what you want to learn further in chemistry. Thank you so much and see you soon. Thank you so much.